Welcome to this video on load flow analysis. This is video number 7. We shall continue with our learning outcome number 2, that is load flow solution. In this video, we shall see how load flow is performed using Gauss-Seidel method, and we will take an example including PV bus now. In the previous video, we have taken on only PQ bus, but in this video we shall include PV bus also, and we will see what changes we have to make in our calculation. So this is the problem which we have considered. In this problem, the first bus, it is given as slack bus, so the voltage is specified. We have to calculate here what is the active power and what is the reactive power to be given by the generator into the system. Bus number 2, it is given as PQ bus. So P and Q are specified as 400 megawatt and 250 MVA. Here we have to calculate the voltage. And the third bus, it is specified as PV bus now, where P is specified, that is 200 megawatt, and V is specified 1.04 per unit. This is the magnitude. So at this bus we have to calculate what is the reactive power to be injected into this system from the generator, and what should be the phase angle of the voltage. So these two parameters we have to calculate. So how to proceed now? As the step 1, it is similar that we have to form a Y bus. Now this how to form Y bus, we have seen it in video number 6. So I won't repeat it again, but if you want, you refer to that video and see how Y bus can be formed for this system. It will be 3 by 3 matrix. Then now you have to assume the voltages for PQ bus and PV bus. So both we have to assume. Now here we have making the assumption that the V2 voltage, the voltage at this bus, which is PQ bus, so we have to assume magnitude, it is assumed 1, and the phase angle is assumed 0. So here it is rectangular, it is written in rectangular form 1.0 plus J0. And V30, the voltage at the third bus, the magnitude is already specified 1.04. Now we have to make assumption for phase angle. So it is here the voltage is assumed 1.04, the magnitude is fixed, and the angle we are making assumption as 0. So it is here it is written in rectangular form 1.04 plus J0. So this is assumption part. Now we have to calculate the voltages. Now we have to calculate the voltage for the PQ bus, that is second bus. So this is the assumption now, 1 at an angle 0, but what is the more correct value we have to calculate. So the equation, already we know that equation we are using for voltage calculation as VI 1 divided by YII in bracket PI minus JQI divided by VI conjugate minus summation YIK VK, and here K varies from 1 to N and K is not equal to I. So this is the equation. Now here to get the voltage at second bus, we have to substitute I is equal to 2 second bus, and N, our system is 3 bus system, so we have to select N value as 3. So after substituting all the values here, so P2 value, it is written here as minus 4. So as already told, now we have to convert it into per unit. So the base value is selected as 100 MVA, so it will be 4 per unit. But now we want the active power to be injected into the bus, so it is written as minus. Similarly, the reactive power 250, it is divided by 100, so we get 2.5, and we want the reactive power to be injected into the bus, so it is taken as minus. So So total it is minus 4 plus j 2.5, and other parameters they are substituted. Okay, and we get the voltage at this bus V2 as 0.97462 j minus j 0.42307. So we have to, in the exam, we have to go up to 4 decimal places. We have to go for 6 decimal places for more accurate answers. So this is how the voltage at the bus 2 is calculated. This is more correct value. Assumption is 1 at an angle 0, but now we have obtained the more correct value. Next, now calculate the reactive power at the PV bus. The third bus we have seen, it is PV bus. So we have to calculate the reactive power. What is the equation here? Already we know what is power flow equation. Pi minus jqi is equal to Vi conjugate and summation yik into vk. Okay, now from this equation k is equal to 1 to n. So from this equation we can calculate this reactive power. Okay, so simply we have to calculate this part. Okay, now here we have to substitute I is equal to 3, that is the third bus, and n we have to take it is 3 bus system, so n value is 3. Now you have to calculate the imaginary, so here it is written minus imaginary of this term, of this entire term will give you the value of q. Now the q value, it is calculated as 1.16 per unit. Now after getting the value of q, that is reactive power at the bus 3, we have to make certain decision, that is check for q limits. Now sometimes uh, now the generation limit, the reactive power generation for a particular generator bus is specified. For example, say Q at the third bus, the generation, reactive power generation, suppose if it is specified something like 0.5, and it should be, it is say 2 per unit. So what mentioned here, that the reactive power at bus 3, the minimum value should be 0.5 and the maximum value is 2. Now in the present case we have obtained it as 1.16. It means that it falls between this range of 0.5 and 2. So we can accept these bus as PV bus, and we can proceed with the calculation of phase angle. This is one case. Another case, suppose if the value of q here, if you get something like 0.25, now you can see here it is less than the minimum value, that is 0.5. In that case, we have to fix this q value at this bus as minimum 0.5, and we have to consider it as PQ bus, and we have to proceed with the calculation, and whatever voltage it is given, that is specified voltage 1.04, we have to drop, and we have to consider it as PQ bus, and we have to proceed as PQ bus, that is calculation of voltage. Another case, suppose if the value of q calculated here, it is come out to be something like 2.5, which is greater than the maximum limit 2. In that case, we have to fix the reactive power at that bus as 2 per unit, and we have to treat this bus as PQ bus, and we have to proceed it as PQ bus by calculating the voltages. Now in the present case, that neither of that two condition hold here, it is within the limit of 0.5 and 2, we have to treat it as PV bus, and now we have to proceed with the calculation of phase angle. So calculate voltage at the PV bus, and from this voltage we have to calculate the similar equation. What we are using the equation for the voltage, and from that equation, now here one important point, here you can see the p value already It is 2. I think here we have written some mistake here. It should be minus 2.0, and it should be here plus j 1.16, because we have to consider here the net active and reactive power injected into the bus. And we got this voltage at this bus is 1.0387. Now if you convert into polar, then we will get the magnitude as 1.04. Angle we will get, we have to consider only the angle. So that angle, it is delta 3 of 1, that is after first iteration. So this is how we have to consider PV bus in the load flow solution. Okay. Now after calculating the reactive power and the phase angle at the PV bus, now we have to check for conversion. That is, for as already I told, we have to find out the difference vector, that is delta V2, and delta V2, it is equal to V2 calculated at the so V2, we can take here V2 at calculated at the first iteration minus V2, and we can get this as a vector, so we can calculate the magnitude of this difference vector. Similarly, we can calculate the magnitude of the difference vector V3, and both of these difference vectors, if they are less than tolerance, then we can stop the iteration and we can go for the power, go for performing load flow. In the case if this difference vector, voltage difference vector, is not less than the tolerance, then we have to proceed with the second iteration. Then we have to calculate the voltage at PQ bus second iteration, and we have to calculate the phase angle at PV bus second iteration, and the procedure repeats. Suppose we assume here that the conversion criteria has met, then we have to proceed with the load flow solution. In the load flow solution, as already discussed in the previous video, that it is altogether we are calculating the line flows, the line current, line flows, bus current, bus flow, bus current and bus power, and also the losses into the system. So the equations also already I have discussed in the previous video, and now if you perform all that things, then here we will get this result. So here it is shown the line flow, that is S12, the line flow from bus number 1 to 2, it is 179.362 megawatt, and the reactive power flow is 118.734 MER. Okay. Now similarly, the line flow from 2 to 1, that is S21, it is 170.968 megawatt and 101.947 MER. Now if we add S12 plus S21, then we will get the loss in this line as 1.8393 megawatt and 16.787 MER. Okay, similarly, the line flows of other line flows and losses of other two lines are also given here, and we can verify the answers. And here you can see 200 megawatt power is injected into the bus, and the reactive power to be injected, it is 146.177 MER from the voltage control bus. Okay, and voltage here at the bus 2 will be getting. So this is how we can perform a load flow using Gauss-Seidel method if there is a PV bus present in the system. So in the next video, we shall take the flow chart, which is very important from the university exam point of view. So I shall take that flow chart in the next video. In this video, up to this only. Thank you very much.